the basic overarching theme for all of these tricks is that it lets you have fewer learnable parameters and less compute and more nonlinearity, which are all sort of nice features to have in your architectures. So if there's any questions about these convolution architecture designs. Too boring or too obvious? OK, so then the next thing is that once you've actually decided on how you want to wire up your stack of convolutions, you actually need to compute them. And there's actually been a lot of work on different ways to implement convolutions. We asked you to implement it on the assignments using for loops, and that, as you may have guessed, doesn't scale too well. So a pretty easy approach that's pretty easy to implement is this idea of an im2call method. So the intuition here is that we know matrix multiplication is really fast. And pretty much for any computing architecture out there, someone has written a really, really well-optimized matrix multiplication routine or library. So the idea of im2call is thinking, well, given that matrix multiplication is really fast, is there some way that we can take this convolution operation and recast it as a matrix multiply? And it turns out that this is actually pretty somewhat easy to do once you think about it. So the idea is that we have an input volume that's h by w by c, and we have a filter bank of convolutions, of convolutional filters. Each one of these is going to be a k by c volume. So it has a k by k receptive field and a depth of c to match the input over here. And we're going to have d of these filters. And then we want to turn this into a matrix multiply problem. So the idea is that we're going to take the first receptive field of the image, which is going to be this k by c region in the input region in the input volume, and we're going to reshape it into this column of k squared by c elements. And then we're going to repeat this for every possible receptive field in the image. So we're going to take this little guy and we're going to shift him over all possible regions in the image. And here I'm just saying that there's going to be maybe n different receptive field locations. So now we've taken our image and we've reshaped it into this giant matrix of n by k squared by c. Anyone see what a potential problem with this might be? Yeah?
You might have a lot more columns than you had.
Yeah, that's true. So this tends to use a lot of memory, right? So any element in this input volume, if it appears in multiple receptive fields, then it's going to be duplicated in multiple of these columns. So, and this is going to get worse the more overlap there is between your receptive fields. But it turns out that in practice, that's actually not too big of a deal, and it works fine. So then we're going to run a similar trick on these convolutional filters. So if you remember what a convolution is doing, we want to take each of these convolutional weights and take inner products with each convolutional weight against each receptive field location in the image. So each of these convolutional weights is this k by c tensor. So we're going to reshape each of those to be a k squared by c row. And now we have d filters, so we get a d by k squared by c matrix. So now this is great. Now this guy contains all the each column is a receptive field, and we have one column per receptive field in the image. And now this matrix has each row is a different weight. So now we can easily compute all of these inner products all at once with this single matrix multiply. And I apologize for these dimensions not working out. I probably should have swapped these two to make it more obvious, but I think you get the idea. So this gives you a d by n result. So that d is our number of output filters, and that n is for all the receptive field locations in the image. So then you play a similar trick to take this and reshape it into your 3D output tensor. And you can actually extend this to mini batches quite easily. If you have a mini batch of n of these elements, you just add more rows and have one set of rows per mini batch element. So this actually is pretty easy to implement. So yeah, question?
How expensive is the reshape operation?
It depends. It depends on your implementation, right? But then you have to worry about things like memory layout and stuff like that to make it fast. But sometimes you'll even do that reshape operation on the GPU, so you can do it in parallel. But as a case study, so this is really easy to implement. So a lot of, if you don't have a convolution technique available and you need to implement one fast, this is probably the one to choose. And if you look at actually Café, in early versions of Café, this is the method that they used for doing convolutions. So this is the convolution forward code for the GPU, the native GPU convolution in Café. So you can see in this red chunk, they're calling into this im2call method. This is taking their input image, right? So this is taking their input image somewhere. This is right. So this is their input image, and then they're going to reshape this, calling this im2call method, and then store it in this column GPU tensor. Then they're going to do a matrix multiply, calling it to cuBLAST to do the matrix multiply, and then add the bias. So that's how I mean, these things tend to work quite well in practice. And also, as another case study, if you remember the fast layers we gave you in the assignments, actually uses this exact same strategy. So here we actually do an im2call operation with some crazy NumPy tricks. And then now we can actually do the convolution inside the fast layers with a single call to the NumPy matrix multiplication. And you saw in your homeworks, this usually gives maybe a couple hundred times faster than using for loops. So this actually works pretty well, and it's pretty easy to implement. Any questions about im2call? Yeah?
How does that work in reverse, like backdrop?
Yeah, so then you have to think about it a little bit. But if you think really hard, you'll realize that the backward pass on a convolution is actually also a convolution, which you may have figured out if you were thinking about it on your homework. But the backward pass of a convolution is actually also a type of convolution over the upstream gradients. So you can actually use a similar type of im2call method for the backward pass as well. The only trick there is that once you do in the backward pass, you need to sum gradients from across overlapping receptive fields in the upstream. So you need to be careful about the call to im. You need to sum in the call to im in the backward pass. And you can actually check out in the fast layers in the homework. It implements that too. Although actually in the fast layers in the homework, the call to im is in Python. I couldn't find a way to get it fast enough in raw NumPy. So there's actually another way that sometimes people use for convolutions, and that's this idea of a fast Fourier transform. So if you have some memories from like a signal processing class or something like that, you might remember this thing called the convolution theorem. And that says that if you have two signals and you want to convolve them, either discretely or continuously with an integral, then taking a convolution of these two signals is the same as, or rather the Fourier transform of the convolutions is the same as the element-wise product of the Fourier transforms. So if you unpack that and stare at the symbols, I think it'll make sense. And if also you might remember from, again, a signal processing class or an algorithms class, that there's this amazing thing called the fast Fourier transform that actually lets us compute Fourier transforms and inverse Fourier transforms really, really fast. You may have seen it. There's versions of this in 1D and 2D, and they're all really fast. So we can actually apply this trick to convolutions. So the way that this works is that first, we're going to use the fast Fourier transform to compute the Fourier transform of the weights, also compute the Fourier transform of our activation map. And now in Fourier space, we just do an element-wise multiplication, which is really, really fast and efficient. And then we just, again, use the fast Fourier transform to do the inverse transform on the output of that element-wise product. And that implements convolutions for us in this kind of cool, fancy, clever way. And this has actually been used, and some folks at Facebook had a paper about this last year, and they actually released a GPU library to compute these things. But the sad thing about these Fourier transforms is that they actually give you really, really big speedups over other methods, but really only for large filters. And when you're working on these small 3x3 filters, the overhead of computing the Fourier transform just dwarfs the computation of doing the computation directly in the input pixel space. And as we just talked about earlier in the lecture, those small convolutions are really, really nice and appealing and great for lots of reasons. So it's a little bit of a shame that this Fourier trick doesn't work out too well in practice. But if for some reason you do want to compute really large convolutions, then this is something you can try. Yeah?
Yeah, so when you're doing that, is there an issue with like spectral resolution on Fourier transform? So in the sense that, you know, if I was going to do this normally in signal processing, I would maybe do a convolution. I'd have like a Hamming window on the convolution before I get it back. Is that something that like matters? Do we care about, or is that something you can use as additional parameters?
I'm not entirely sure. I'm actually not too involved in Fourier stuff. But I imagine if you think it's a problem, it's probably a problem. Yeah, although another thing to point out is that one kind of downside about Fourier transforms convolutions is that they don't handle striding too well. So for normal when you're computing strided convolutions in sort of normal input space, you only compute a small subset of those inner products. So you actually save a lot of computation when you do strided convolutions directly on the input space. But the way you tend to implement strided convolutions in Fourier transform space is you just compute the whole thing and then you throw out part of the data. So that ends up not being very efficient. So there's another trick that has not really become too widely known yet, but I really like it, so I thought I wanted to talk about it. So you may remember from an algorithms class something called Strasson's algorithm, right? So there's this idea that when you do a naive matrix multiplication of two n by n matrices, kind of if you count up all the multiplications and additions that you need to do, it's going to take n cubed operations. And Strasson's algorithm is this like really crazy thing where you compute all these crazy intermediates and it somehow magically works out to compute the output asymptotically faster than the naive method. And from im2col, we know that matrix multiplication is this. We can implement convolution as matrix multiplication. So intuitively, you might expect that these similar types of tricks might theoretically maybe be applicable to convolution. And it turns out they are. So there's this really cool paper that just came out over the summer where these two guys worked out very explicitly some very special cases for 3x3 convolutions. And it involves this, obviously I'm not going to go into details here, but it's a similar flavor to Strasson's algorithm, where you're computing very clever intermediates and then recombining them to actually save a lot on the computation. And these guys are actually really, really intense, and they're not just mathematicians. They actually wrote also highly, highly optimized CUDA kernels to compute these things, and were able to speed up VGG by a factor of 2. So that's really, really impressive. So I think that this type of trick might become pretty popular in the future. But for the time being, I think it's not very widely used. But these numbers are crazy. And especially for small batch sizes, they're getting a 6x speed up on VGG. So that's really, really impressive. And I think it's a really cool method. The downside is that you kind of have to work out these explicit special cases for each different size of convolution. But maybe if we only care about 3x3 convolutions, that's not such a big deal. So the recap on computing convolutions in practice is that the sort of the really fast, easy, quick, and dirty way to implement these things is im2col. Matrix multiplication is fast. It's usually not too hard to implement these things. So if for some reason you really need to implement convolutions yourself, I'd really recommend im2col. FFT is something that, coming from signal processing, you might think would be really cool and really useful. But it turns out that it does give speedups, but only for big filters. So it's not as useful as you might have hoped. But there is hope because these fast algorithms are really good at small filters. And there already exists code somewhere in the world to do it. So hopefully these things will catch on and become more widely used. So if there's any questions about computing convolutions? No? OK. So next, we're going to talk about some implementation details. So first, I have a question. How many of you guys have ever built your own computer? Some? OK. So you guys are prevented from answering on this next slide. So who can spot the CPU? Anyone want to point it out? Yeah, so the CPU is this little guy. Right, so actually this thing is actually, a lot of it is the cooler. So the CPU itself is a little tiny part inside of here. A lot of this is actually the heat sink and the cooling. So next, who can spot the GPU? Yeah, it's the thing that says GeForce on it. So this GPU is for one thing, it's much larger than the CPU. So it maybe is more powerful, I don't know. But at least it's taking up more space in the case. So that's kind of an indication that something exciting is happening. So I have another question. Any of you guys, play video games? Okay. Then you probably have opinions about this. So it turns out a lot of people in machine learning and deep learning have really strong opinions too, and most people are on this side. So NVIDIA is actually much, much more widely used than AMD for using GPUs in practice. And the reason is that NVIDIA has really done a lot in the last couple years to really dive into deep learning and make it a really core part of their focus. So as a cool example of that, last year at GTC, which is NVIDIA's sort of yearly big, gigantic conference where they announce new products, Jensen Huang, who's the CEO of NVIDIA, and actually also a Stanford alum, introduced this latest and greatest amazing new GPU called the Titan X, like their flagship thing. And the benchmark he used to sell it was how fast it can train AlexNet. So this was crazy. This was a gigantic room with like hundreds and hundreds of people and journalists and like this gigantic, highly polished presentation. And the CEO of NVIDIA was talking about AlexNet and convolutions. And I thought that was really exciting. And it kind of shows you that NVIDIA really cares a lot about getting these things to work. And they've pushed a lot of their efforts into making it work. So just to give you an idea, a CPU, as you probably know, is really good at fast sequential processing, and they tend to have a small number of cores. Ones in your laptop probably have like maybe between 1 and 4 cores, and big things on a server might have up to 16 cores-ish. And these things are really good at computing things really, really fast and in sequence. GPUs, on the other hand, tend to have many, many, many cores. For a big guy like a Titan X, it can have up to thousands of cores. But each core can do less. They tend to run at a lower clock speed and be able to do less per instruction cycle. So these GPUs, again, were originally developed for processing graphics processing units. And so they're really good at doing sort of highly parallelized operations, where you want to do many, many things in parallel independently. And since they were originally designed for computer graphics, but since then, they've sort of evolved as a more general computing platform. So there are different frameworks that allow you to write generic code to run directly on the GPU. So from NVIDIA, we have this framework called CUDA that lets you write a variant of C to actually write code that runs directly on the GPU. And there's a similar framework called OpenCL that works on pretty much any computational platform. But I mean, open standards are nice, and it's quite nice that OpenCL works everywhere. But in practice, CUDA tends to be a lot more performant and have a little bit nicer library support. So at least for deep learning, most people use CUDA instead. And if you're interested in actually learning how to write GPU code yourself, there's a really cool Udacity course. It's pretty cool. They have fun assignments, all that lets you write code to run things on the GPU. Although in practice, if all you want to do is train ComNets and do research and that sort of thing, you end up usually not having to write any of this code yourself. You just rely on external libraries. Yeah?
Is cuDNN kind of like Caffe and Torch, or what does it provide?
Yeah, so cuDNN is, I'll talk about that in a minute. Right, so CUDA is like this raw, so cuDNN is a higher level library, kind of like cuBLAS. Right, so one thing that GPUs are really, really good at is matrix multiplication. So here's a benchmark. I mean, this is from NVIDIA's website, so it's a little bit biased. But this is showing matrix multiplication time as a function of matrix size on a pretty beefy CPU. So this is a 12-core guy that would live in a server. So that's like quite a healthy CPU. And this is running the same size matrix multiply on a Tesla K40, which is a pretty beefy GPU. And it's much faster. I mean, that's no big surprise, right? And GPUs are also really good at convolutions. So as you mentioned, NVIDIA has a library called cuDNN that is specifically optimized CUDA kernels for convolution. So compared to CPU, I mean, it's way faster. And this is actually comparing the im2call convolutions from Caffe with the cuDNN convolutions. I think these graphs are actually from the first version of cuDNN. Version 4 just came out maybe a week ago. But this is the only version where they actually had a CPU benchmark. Since then, the benchmarks have only been against previous versions. So it's gotten a lot faster since here. But the way this fits in is that something like cuBLAS or cuDNN is a C library. So it provides functions in C that just sort of abstract away the GPU as a C library. So if you have a tensor sort of in memory in C, you can just pass a pointer to the cuDNN library, and it'll return it'll run it on the GPU maybe asynchronously and return the result. So frameworks like Caffe and Torch all have now integrated the cuDNN stuff into their own frameworks. So you can utilize these efficient convolutions in any of these frameworks now. But the problem is that even once we have these really powerful GPUs, training big models is still kind of slow. So VGGNet was famously trained for something like 2 to 3 weeks on 4 Titan Blacks, and those aren't cheap. And there was actually a re-implementation of ResNet recently. There's a really cool write-up, there's a really cool blog post describing it here. And they actually retrained the ResNet 101 layer model, and it also took about 2 weeks to train on 4 GPUs. So that's not good. And one way that people, the easy way to split up training across multiple GPUs is just to split your mini batch across the GPUs. So normally, you might have, especially for something like VGG, it takes a lot of memory. So you can't compute with very large mini batch sizes on a single GPU. So what you'll do is you'll have a mini batch of images, maybe of 128 or something like that. You'll split the mini batch into 4 equal chunks. On each GPU, you'll compute a forward and a backward pass for that mini batch. And you'll compute gradients on the weights. You'll sum those weights inside. You'll sum those weights after all 4 GPUs finish and make an update to your model. So this is a really simple way that people tend to implement distribution on GPUs. Yeah?
Just in theory, isn't this what TensorFlow is supposed to be really good at? It's like automating across a bunch of GPUs. Yeah. So one of the cool pitches of TensorFlow is they claim that they can automate this process and really efficiently distribute it, which is really exciting, I think. But I haven't played around with it too much myself yet. And also, at least in Torch, there's a data parallel layer that you can just drop in and use that'll sort of automatically do this type of parallelism very easily. A slightly more complex idea for multi-GPU training actually comes from Alex Krichevsky of AlexNet fame. That's kind of a cool, kind of a funny title. But the idea, is that we want to actually do data parallelism on the lower layers. So on the lower layers, we'll take our image mini batch, split it up across 2 GPUs, and GPU 1 will compute the convolutions for the first part of the mini batch, and at least this convolution part will be distributed equally across the GPUs. But once you get to the fully connected layers, he found it's actually more efficient because those are just really big matrix multiplies, then it's more efficient to actually have the GPUs work together to compute this matrix multiply. So this is kind of a cool trick. It's not very commonly used, but I thought it's fun to mention. Another idea from Google is before there was TensorFlow, they had this thing called Disbelief, which was their previous system, which was entirely CPU based, which from the benchmarks a few slides ago, you can imagine was going to be really slow. But actually, the first version of GoogleNet was all trained in Disbelief on CPU. So they had to do massive amounts of distribution on CPU to get these things to train. So here, there's this cool paper from Jeff Dean a couple years ago that describes this in a lot more detail. But you use data parallelism, or you have each machine have an independent copy of the model. And each machine is computing forward and backward on batches of data. But now you actually have this parameter server that's storing the parameters of the model. And these independent workers are making communication with the parameter server to make updates on the model. And they contrast this with model parallelism, which is where you have one big model and you have different workers computing different parts of the model. So in Disbelief, they really did a really good job optimizing this to work really well across many CPUs and many machines. But now they have TensorFlow, which hopefully should do these things more automatically. And once you're doing these updates, there's this idea between asynchronous SGD and synchronous SGD. So synchronous SGD is kind of the thing, like the naive thing you might expect. You have a mini batch, you split it up across multiple workers. Each worker does forward and backward, computes gradients. Then you add up all the gradients and make a single model update.
This will sort of exactly simulate just computing that mini batch on a larger machine, but it could be kind of slow since you have to synchronize across machines. This tends to not be too much of a big deal when you're working with multiple GPUs on a single node, but once you're distributing this across many, many CPUs, that synchronization can actually be quite expensive. So instead, at least, they also have this concept of asynchronous SGD, where each model is just sort of making updates to its own copy of the parameters, and those have some notion of eventual consistency, where they sometimes periodically synchronize with each other. And it seems really complicated and hard to debug, but they got it to work. So that's pretty cool. And one of the really cool pitches, so these two figures are both from the TensorFlow paper. And one of the pitches of TensorFlow is that it should really make this type of distribution much more transparent to the user. That if you do happen to have access to a big cluster of GPUs and CPUs and whatnot, TensorFlow should automatically be able to figure out the best way to do these kinds of distributions, combining data and model parallelism, and just do it all for you. So that's really cool, and I think that's the really exciting part about TensorFlow. Any questions about distributed training? Yeah.
Do you have any thoughts on CNTK?
On CNTK? I haven't taken a look at it yet. Okay, so next, there's a couple bottlenecks you should be aware of in practice. So like usually when you're training these things, like this distributed stuff is nice and great, but you can actually go a long way with just a single GPU on a single machine. And there's a lot of bottlenecks that can get in the way. One is the communication between the CPU and the GPU. Actually, in a lot of cases, especially when the data is small, the most expensive part of the pipeline is copying the data onto the GPU and then copying it back. Once you get things onto the GPU, you can do computation really, really fast and efficiently. But the copying is the really slow part. So one idea is you want to make sure to avoid the memory copy. Like one thing that sometimes you see is like at each layer of the network is copying back and forth from CPU to GPU, and that'll be really inefficient and slow everything down. So ideally, you want the whole forward and backward pass to run all on the GPU at once. Another thing you'll sometimes see is a multi-threaded approach, where you'll have a CPU thread that is prefetching data off disk or off memory in one thread in the background, possibly also applying data augmentations online. And then this background CPU thread will be sort of preparing mini batches and possibly also shipping them over to GPU. So you can kind of coordinate this loading of data and computing preprocessing and shipping mini batch data to the GPU and actually doing the computations. And actually, you can get pretty involved with coordinating all these things in a multi-threaded way. And that can give you some good speed-ups. Caffe in particular, I think, already implements this prefetching data layer for certain types of data storages. And in other frameworks, you just have to roll your own. Another problem is the CPU disk bottleneck. So these things are kind of slow. They're cheap and they're big, but they actually are not the best. So these are hard disks that now these solid-state drives are much more common. But the problem is that solid-state drives are smaller and more expensive, but they're a lot faster, so they get used a lot in practice. So what's really, although one common feature to both hard disks and solid-state drives is that they work best when you're reading data sequentially off the disk. So a lot of times what you'll, so one thing that would be really bad, for example, is to have a big folder full of JPEG images. Because now each of these images could be located in different parts on the disk. So it could be you'd have to do a random seek to read any individual JPEG image. And now also, once you read the JPEG, you'd have to decompress it into pixels. So that's quite inefficient. So what you'll see a lot of times in practice is that you'll actually pre-process your data by decompressing it and just writing out the raw pixels for your entire data set in one giant contiguous file to disk. So that takes a lot of disk space, but we do it anyway because it's all for the good of the ComNets. Right? So this is so in Caffe we do this with like a level DB is one commonly used format. I also use HDF5 files a lot for this. But the idea is that you want to just get your data all sequentially on disk and already turned into pixels. So then when you're training, you can't store all your data in memory. You have to read it off disk. And you want to make that read as fast as possible. And again, with clever amounts of prefetching and multi-threaded stuff, you might have one thread fetching data off disk while other computation is happening in the background. Another thing to keep in mind is GPU memory bottlenecks. So GPUs, big ones have a lot of memory, but not that much. So the biggest GPUs you can buy right now are the Titan X and the K40 have 12 gigs of memory. And that's pretty much as big as you're going to get right now. Next gen should be bigger. But you can actually bump up against this limit without too much trouble, especially if you're training something like a ResNet or a VGG, or if you're having recurrent networks for very, 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 very long time steps. It's actually not too hard to bump up against this memory limit. So that's something you need to keep in mind when you're training these things. And some of these points about these efficient convolutions and cleverly creating architectures actually helps with this memory as well. If you can have a bigger, more powerful model with smaller amounts of, and use less memory, then you'll be able to train things faster and use bigger mini batches and everything is good. And even just for sense of scale, AlexNet is pretty small compared to a lot of the models that are state-of-the-art now. But AlexNet with a 256 batch size already takes about 3 gigabytes of GPU memory. So once you move to these bigger networks, it's actually not too hard to bump up against the 12 gig limit. So another thing we should talk about is floating point precision. So when I'm writing code, a lot of times I like to imagine that these things are just real numbers and they just work. But in practice, that's not true. And you need to think about things like how many bits of floating point are you using. So a lot of types of numeric code that you might write sort of is with a double precision by default. So this is using 64 bits. And a lot of, also more commonly used for deep learning is this idea of single precision. So this is only 32 bits. So the idea is that if each number takes fewer bits, then you can store more of those numbers within the same amount of memory. So that's good. And also with fewer bits, you need less compute to operate on those numbers. So that's also good. So in general, we would like to have smaller data types because they're faster to compute and they use less memory. And as a case study, this was actually even an issue on the homework. So you may have noticed that in NumPy, the default data type is this 64-bit double precision. But for all of these models that we provided you on the homework, we had this cast to a 32-bit floating point number. And you can actually go back on the homework and try switching between these two. And you'll see that switching to the 32-bit actually gives you some decent speedups. So then the obvious question is that if 32 bits are better than 64 bits, then maybe we can use less than that, right? So there's this right. So there's this idea of using 16 bits. What's the best order to do these? Right. OK, so in addition to 32-bit floating point, there's also a standard for 16-bit floating point, which is sometimes called a half precision. And actually, recent versions of cuDNN do support computing things in half precision, so that's cool. And actually, there are some other existing implementations from a company called Nirvana, who also has these 16-bit implementations. So these are the fastest convolutions out there right now. So there's this nice GitHub repo that has different kinds of ComNet benchmarks for different types of convolutions and frameworks and everything. And pretty much everything winning all of these benchmarks right now are these 16-bit floating point operations from Nirvana, which is not surprising, right? Because again, you have fewer bits, so it's faster to compute with them. But right now, there's actually not yet framework support in things like Caffe or Torch for utilizing this 16-bit computation. But it should be coming very soon. But the problem is that even if we can compute, it's pretty obvious that if you have 16-bit numbers, you can compute with them very fast. But once you get to 16-bit, then you might actually be worried about numeric precision. Because 2 to the 16 is not that big of a number anymore. So there's actually not too many real numbers you can even represent. So there was this paper from a couple years ago that it did some experiments on low precision floating point. And they found that actually just using, so they actually used a fixed width rather than a floating point implementation. And they found that actually with these with this sort of naive implementation of these low precision methods, the networks had a hard time converging. Probably due to these low precision numeric issues that kind of accumulate over multiple rounds of multiplication and whatnot. But they found a simple trick was actually this idea of stochastic rounding. So some of their multiplications so all their parameters and activations are stored in 16-bit, but when they perform a multiplication, they upconvert to a slightly higher precision floating point value, and then they round that back down to a lower precision. And actually doing that rounding in a stochastic way, that is not rounding to the nearest number, but probabilistically rounding to different numbers depending on how close you are, tends to work better in practice. So they found that, for example, when you're using, so these were 16-bit fixed point numbers with 2 bits for integers and between 12 and 14 bits for the floating point, for the fractional part, that when you use this idea of always rounding to the nearest number, these networks tend to diverge. But when you use these stochastic rounding techniques, then you can actually get these networks to converge quite nicely, even with these very low precision floating point numbers. But you might want to ask, well, 16-bit is great, but can we go even lower than that? So there was another paper in 2015 that got down to 10 and 12 bits. So here, from the previous paper, we already had this intuition that maybe when you're using very low precision floating point numbers, you actually need to use more precision in some parts of the network and lower precision in other parts of the network. So in this paper, they were able to get away with storing the activations in 10-bit values and computing gradients using 12 bits. And they got this to work, which is pretty amazing. But anyone think that that's the limit? Can we go further?
One bit.
Yes. So there was actually a paper just last week. So this is actually from the same author as the previous paper. And this is crazy. I was amazed about this. And here the idea is that all activations and weights of the network use only 1 bit. They're either 1 or -1. So that's pretty fast to compute. Now you don't even really have to do multiplication. You can just do like bitwise XNOR to multiply those. So that's pretty cool. But the trick is that on the forward pass, all of the gradients and activations are either 1 or -1. So the forward pass is super, super fast and efficient. But now on the backward pass, they actually compute gradients using a higher precision. And then these higher precision gradients are used to actually make updates to these single bit parameters. So it's actually a really cool paper, and I'd encourage you to check it out. But the pitch is that maybe at training time, you can afford to use maybe more floating point precision, but then at test time, you want your network to be super, super fast and all binary. So I think this is a really, really cool idea that, the paper just came out 2 weeks ago, so I don't know, but I think it's a pretty cool thing. So the recap from implementation details is that overall GPUs are much, much faster than CPUs. Sometimes people use distributed training. Distributing over multiple GPUs in one system is pretty common. If you're Google and using TensorFlow, then distributing over multiple nodes is maybe more common. Be aware of different kinds of bottlenecks between the CPU and the GPU, between the GPU and the disk, and between the GPU memory. And also pay attention to floating point precision. It might not be the most glamorous thing, but it actually, I think, makes huge differences in practice. And maybe binary nets will be the next big thing. That'd be pretty exciting. So yeah, just to recap everything we talked about today, that we talked about data augmentation as a trick for improving when you have small data sets and help prevent overfitting. We talked about transfer learning as a way to initialize from existing models to help with your training. We talked in a lot of detail about convolutions, both how to combine them to make efficient models and how to compute them. And we talked about all these implementation details. So I think that's all we have for today. So if there's any last minute questions. All right, so I guess we're done a couple minutes early, and the midterms are